Hello class, in this video I'll be showing you an application of average rate of change and instantaneous rate of change. Let's begin. Before I start the problem, there's one more piece of information that you need to know. And that is the instantaneous rate of change of a function at a given point is the approximate change in the function when the distance from the given point is exactly 1 unit. Now let's take a look at an example. Suppose the monthly sales, n of p, of a certain box of cereal can be modeled using the function n of p is equal to 100 minus 4p squared, where p is the dollars per box. Find the average rate of change in demand for a change in price from $3 to $4. Okay, so the problem is asking for average rate of change, so we will use the average rate of change formula. And that will be n of 4 minus n of 3, all divided by 4 minus 3. In Desmus, you can evaluate n of 4 and n of 3. n of 4 will equal 36, and n of 3 will equal 64. So the average rate of change will be 36 minus 64, all divided by 4 minus 3, and this will equal negative 28. Now for the label. In the numerator, you will have boxes of cereal. In the denominator, it will be $1. So the average rate of change is negative 28 boxes of cereal per $1. Now to interpret the results. If the price of a box of cereal increases from $3 to $4, the monthly demand for the box of cereal will decrease by exactly 28 boxes per month. Now, the reason why I use the word exactly 28 boxes and not approximately is because the span from 3 to 4 is exactly 1. And when dealing with average rate of change, if the span of the interval is exactly 1, then the change in the function is an exact change. Now on to part C. Find the instantaneous rate of change in demand when the price is $3. Since the problem is asking for an instantaneous rate of change, we will use the instantaneous rate of change formula. So we'll have the limit as h approaches 0 of n of p plus h minus n of p, all divided by h, and we're going to evaluate this formula when p is equal to 3. So we have the limit as h approaches 0 of n of 3 plus h minus n of 3, all divided by h. Over here to the right, I will evaluate n of 3 plus h, and this means wherever you see a p in the function, you're going to substitute 3 plus h. So this will be 100 minus 4 times 3 plus h all squared. This will be 100 minus 4 times, now if we expand 3 plus h all squared, this will be 9 plus 6h plus h squared. Distributing the negative 4 and combining like terms will yield 64 minus 24h minus 4h squared. And we found n of 3 in part A, that was equal to 64. So now I will substitute 64 minus 24h minus 4h squared in for n of 3 plus h, and I will substitute 64 in for n of 3. After the substitution, you'll notice that the 64's zero out, and I'm going to factor an h out of the numerator. So this will be the limit as h approaches 0 of h times the quantity negative 24 minus 4h, all divided by h. Now the numerator and the denominator have a common factor of h, so I will divide those out, and that's 1. So this is equal to negative 24 minus 0, which is equal to negative 24. And the label will be the same label as in part A. So this will be negative 24 boxes of cereal per $1. Now to interpret the results. If the price of boxes of cereal increases from $3 to $4, 4 is exactly 1 unit more than 3, the monthly demand for the box of cereal will decrease by approximately 24 boxes per month. The reason why we use the word approximately in this interpretation, as opposed to exactly, is because we are talking about instantaneous rate of change. And when dealing with instantaneous rate of change, we are only given 1 point. And if we're only given 1 point, we can only approximate the change in the function when that 1 point is increased by 1 unit. So in this example, the point that was given was $3. When $3 is increased by 1 unit, that is $4. So if the price of a box of cereal increases from $3 to $4, the monthly demand for the box of cereal will decrease by approximately 24 boxes per month. And we are done.